my name is William Alexander, and today I will be showing y'all through our second lab of voltage and electric field in a coaxial cable. My lab partners are Edmund Ho, Crescentia Sugiyama, and Diana Lau. The purpose for this lab is to test two different methods for determining the linear charge density in the electric field emanating from this central wire. Our first method is derived from the Gauss law, and our second method is derived from the definition of electrostatic potential. Now, our hypothesis is that both of these derived equations should give us the same linear charge density. And to that end, we have this equipment set up. We have a central wire through which the electricity will flow through and the electric field will emanate from. And we have a shield to contain our experiment. And we've got a power supply up here set to 15 volts. So the central wire will start at 15 volts, and as it gets farther away, it will decrease until it hits 0 at the shield. And we have a voltmeter with which to measure the voltage as we go farther from the central wire. Now, there are 8 centimeters between the edge of the central wire and the inner lining of the shield. And it is in that area that we will take our measurements. And so we've decided to take our measurements in half centimeter increments. To do that, we can just hold down to the shift button and use an arrow key to move half centimeter intervals. We can press M to leave points, and we will record the distance from the central wire along with the associated amount of voltage, and we will use that as the data for our equations. So here we have our data sheet. We have our points and radial distances and voltage at those distances. We have our acknowledged uncertainties for both radial distance and the voltage. So using this raw data, we will derive the information that we need to plug into our equations. Calculation table 1 for the Gauss law and calculation table 2 for the definition of electrostatic potential. So for calculation table 1, we will begin with finding Rn, which is Rn plus 1 plus Rn divided by 2. This will be the middle distance between points. And then we have ENR, which is volts per centimeter. This will be Vn plus 1 minus Vn divided by Rn plus 1 minus Rn. And then we have 1 over Rn, which is simply the reciprocal of our column in Rn. Now we will plot a graph of ENR versus 1 over Rn. As you can see here, we have our points plotted in. We have a trend line to take the average slope of all of our points. And we have the equation of that slope right here, where we have a slope of 4.6019. And so now we move on to calculation table 2, which is for our electrostatic potential. We need to derive the log of R naught over R and the voltage at each point, which is simply what the voltage we've already recorded for our points. So for log of R naught over R, we simply take the natural log of 8, which is our R naught it is 8 centimeters between the central wire and the shield. So we have 8 divided by the distance away from the central wire. And we take the natural log of that. Then we'll plot out in a graph log of R naught over R versus VR. And as you can see here, we have a similar graph as our previous. We have the points, we have a trend line, and we have the slope. Now, each of these slopes are vital components in our final calculation, which are our derived equations. And here we have our final calculations. Our linear charge density by way of ER is here, and our linear charge density as by the way of VR is here. Now these two results are very close, and we believe them to be roughly equivalent. They fall within our uncertainties, and it was known from the onset of the experiment that we would not get a perfect answer between them due to the fact that the relationship between these two equations can only be charted as an approximation. Our conclusion is that we believe our hypothesis was true and our experiment a success. We appear to have arrived at the same or at least similar linear charge density from two different equations. So that was our experiment today. Thank you for watching.